Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 16 physics series where we are discussing each and every chapter. We have started with chapters from second PU and we have already completed a few chapters. Today we are continuing with Magnetism and Matter part 2. We have already completed one part on this chapter. If you have not seen that, you can go back to our channel and check all the videos that we have done. And now if you want all the updates from our channel, you can join our WhatsApp group. Okay, that there we will be sharing all the updates related to all the KCET 2025 things. Now let's start with today's chapter. What all we are going to cover into this chapter. First we will be covering magnetization, then we will be covering magnetic intensity, another important concept, magnetic properties of materials, very important concept, and then time period of oscillating magnetic needle. Okay, these all are we are going to cover in today's lecture. Now remember that Earth's magnetism, that was part of the syllabus which is currently deleted. So any questions related to Earth's magnetism will not be coming to your upcoming 2025. In the previous year question we will be doing PYQs tomorrow, but in PYQs for this chapter most of the questions were actually coming from Magnetism and Matter chapter was coming from Earth's magnetism, so that is now deleted. So Earth's magnetism will no longer be coming to your question paper, but some concepts which are we are going to cover, I will be doing some stress on whatever new question that might come from this chapter. So it will be unknown territory, but I am here to help you completely to understand this chapter, and all the two questions that is coming from this chapter you will be able to answer that. Okay, let's start with first part, magnetization. A circulating electron in an atom has a magnetic moment. In a bulk material, these moments add up vectorially and they can give a net magnetic moment which is not zero. So what is the meaning of that? We know that an electron rotating in an orbit, they give rise to magnetic moment, right? We have learned that if there is a current in a circular loop, okay, suppose the current is flowing in this direction, okay, then we can find the polarity of the magnetic moment, right? So if the current is in this direction, there will be a north pole, and if you look from below, you will get a south pole. Okay, so similarly an atom, this is circular loop, right? Similarly in an atom also, an electron is rotating, there is a positively charged at the center and an electron is rotating. Now if there is a single electron rotating in an orbit, okay, this can sometimes gives rise to magnetic moment. Okay, now if there are two electrons, one is rotating in this direction, another rotating in opposite direction, then they sometimes cancel each other's magnetic moment. But if they do not cancel each other, suppose there is a lone pair, okay, single electron, okay, in that case that electron, whatever magnetic moment is there due to that single electron, that is not zero. Okay, and then we define something called magnetization, capital M. Okay, don't get confused with the magnetic moment. Magnetization is also denoted by capital M, magnetic moment is also denoted by capital M, but only thing is the difference is quite similar. Now magnetization is defined by net magnetic moment. Okay, it's kind of magnetic moment, but magnetic moment per unit volume. Okay, net magnetic moment. So suppose in a unit volume, that is 1 centimeter by 1 centimeter, 1 meter cube, all the atoms that is located, okay, and the net magnetic moment due to all the atoms located inside that atom, then that is gives rise to magnetization. Okay, and M is a vector with dimensions L inverse ampere, okay, L inverse current, so that is length inverse current. Okay, now and its unit is ampere per meter, so it is a very interesting unit. Okay, so unit, do look for units, that is also sometimes they might ask you, because this is an uncommon quantity, okay, and they might ask you as the what is the unit of magnetization. Okay, so be careful. Magnetization, capital M, its unit is ampere per meter. Okay, Don't get confused with current density. Okay, current density is ampere per meter square, magnetization is ampere per meter. Okay, now the ratio of magnetic field at the center of a current carrying circular coil to its magnetic moment is x. If the current and the radius both are doubled, the new ratio will become. So what they have asked you? They have asked you to find the magnetic moment times the ratio of magnetic field is to magnetic moment. Okay, now we know that B at the center of a coil is given by mu naught r square by 2 r square plus x square, right? Now for at the center x is 0, so we can write this to the power 3 by 2, sorry, right? So we can write this as mu naught divided by 2r, right? Mu naught I. There was a I here, obviously current carrying loop, so current should be there. So current carrying loop, mu naught, let me write the I here. So mu naught I by 2r is the magnetic field. Now what is magnetic moment? We know that magnetic moment is basically net magnetic moment. We have just seen the formula is its magnetic moment. It is not magnetization. So magnetic moment is given by area times I. So it is pi r square I, right? Now they have given you B by magnetic moment is basically x, right? So initially what is the value? Mu naught I by 2r, okay, divided by pi r square I equals to x. So the value of x, we can write it here to be mu naught by 2 pi r square, right? So x equals to mu naught by 2 pi, sorry, r square times another r. Okay, so this 2r will come down, right? So 2r, so it will become mu naught by 2 pi r cube, right? Now x is basically proportional to 1 by r cube, right? Now if the radius and current both are double, it does not depend on current at all. Only thing, it depends on the cube root of radius, that is inversely proportional to cube root of radius. So if you increase the radius, radius doubled, then this x dash will become x by r cube. Okay, so basically x by other things, other ratio will be cancelled, so it will become doubled only, so it will become x by 8. Okay, double means you have to put r, instead of r you have to put 2r, so it will become 8r cube. So the rest of the r cube will be cancelled. You can find the ratio, it will be x by 8, right? So correct answer is option B. Very interesting question from previous year. Now let's look into a very important concept, magnetic intensity. Okay, magnetic intensity is something which is defined like this. Okay, now inside, when you are using a solenoid, suppose we know that solenoid has a magnetic moment. Okay, here M is obviously the magnetization. Now when you are considering a solenoid, okay, empty solenoid, the formula is simple, right? For an empty solenoid, B was mu naught Ni, right? Now if the solenoid is not empty, if you put something, some material inside the solenoid, some magnetic material inside the solenoid, okay, then it is no longer mu naught Ni. Okay, it has to be a little bit different formula. For that we define another vector quantity called magnetic intensity. It is directly related to the magnetic field. Okay, you can say this is a cousin brother of magnetic field, right? Now the dimension of magnetic intensity and M are same. Obviously you can see that H equals to B by mu naught minus M. So M and H should be of the same dimension, right? So and the unit is ampere per meter, same as magnetic magnetization. So magnetic intensity and magnetization both have same unit, ampere per meter. Okay, and from this relationship what we can do, we can multiply everything by mu naught, and if we take minus m mu naught m to the left hand side, then we can write this as B equals to mu naught H plus m, or in the other word what you can do from here, B by mu naught equals to H plus m, right? We can write this m will come on the left hand side, and then if we reverse it, you can write this like this, and then we can calculate B as mu naught H plus m. Okay, so H plus m together gives the times with magnetic field, mu naught gives the magnetic field. Okay. Now, if a bar now let us go back and solve yesterday's homework problems. If a bar magnet of magnetic moment m is cut along the breadth into two equal parts, then what will be the change in its magnetic moment of the magnet? So we have a magnet. I have solved one similar problem. These problems are very common, and magnetic moment is given. So suppose magnetic monopole is small m's. Okay, both of them are same. Now what they have asked you, they have cut it into from the breadth. Okay, if they cut it from the breadth, so initially suppose the length was 2L. Initially length was 2L. Now both the length are L. Both the lengths are L. Now as soon as you cut it, there will be another m appearing here, another m appearing here. I am just writing the magnitude. I am not using plus minus like in case of charges. Okay, so now initially what was the magnetic moment? Magnetic moment was m times 2L, right? Now what is the new magnetic moment? New magnetic moment is m times L. So what is this? This is basically m by 2. Okay, so it is m by 2. Correct answer is m by 2. So no matter how you cut it from here or you cut it from here, okay, it will be always m by 2, right? Now let's move on. Next homework problem, very interesting question. If magnetic monopoles m existed, okay, assuming that monopole m existed, how would the Gauss's law of magnetism be modified? So we know that in case of electricity, basically it is a comparison of electricity. In case of electricity, E dot ds vector equals to q enclosed by epsilon naught, right? So they have asked you how it would have changed. Right now, in case of electricity, the constant was 1 by 4 pi epsilon naught. If you remember, corresponding magnetic constant is mu naught by 4 pi. Okay, so in the case of electric field, it was 1 by epsilon naught. So in case of magnetic field, it should be mu naught. Okay, so the correct answer is option C, mu naught m. Same, instead of Q, you have to use magnetic field m. Okay, instead of magnetic monopole m, instead of electric field, you have to use magnetic field B. Rest of the formula is same, right? So m enclosed or normal m, whatever you can write. Okay, whatever. Obviously, the m inside that surface. Okay, so that inside that surface should be mu naught m, not m by mu naught. Okay, be careful. Most students generally misunderstand that and answer m by mu naught. This is a very common question. Maybe not for KCET, but maybe it will come. Who knows, right? Now let us look into magnetic susceptibility. This is a very important and a long part. So we will break it down one by one. Now magnetization can be written as in terms of a constant chi times H vector. Okay, chi is a dimensionless quantity. Basically, I already told you m and h are of same dimension, right? M and h are of the same dimension, then we can use this chi, another constant, as a dimensionless quantity. It is appropriately called magnetic susceptibility. Very important concept. Magnetic susceptibility, what does it mean? It means it measures how a magnetic material responds to an external field. Very important. Okay, how a magnetic material, only magnetic material. Okay, other than that, we will see how it actually changes in later part of the video. Okay, how a magnetic material responds to external field. So if you apply external field, what will happen to that material? Will it attract that magnetic field lines? Will it repel the magnetic field lines? Or what will happen to that material? That is the main point of this term, magnetic susceptibility. How much susceptible this is to the external magnetic field. Okay, susceptible means how much you can resist, how much you can adapt. That is called susceptibility. Okay, we already know that B is equal to mu naught H plus M. Also, we have defined one more quantity that magnetization can be written as magnetic susceptibility times H vector. So let us put this value inside this. So what we will get? We will get B equals to mu naught H plus chi. This is the pronunciation for this is chi. Okay, remember that pronunciation for this is not X, it's chi. Okay, now we can take this H vector common, so we can write mu naught times 1 plus chi H vector. Now we can define this, we can say that this is basically mu naught. What is mu naught? Mu R. Mu R is the relative permeability. Okay, in case of electric field we used a similar term epsilon R. Okay, later on we have seen this is also dielectric constant, right? The same thing is dielectric constant, also we have called it relative permittivity. Now mu naught is permeability of free space. Okay, mu naught is permeability of free space, mu R is permeability of any medium. Okay, so everything is concentrated on the fact that we are considering a solenoid and the solenoid is not empty, it has some material inside it. That's it. Okay, only for them we will use this concept. Otherwise, if it is empty, normal B is sufficient. But why that is so, that also we will see why we are using some material inside a solenoid to explore. Okay, now B can be written this as mu. What is mu? Mu is the permeability of that medium. Okay, so whatever material we are using inside that, so that material is mu, its relative permeability is mu R. Okay, relative permeability means permeability divided by permeability of free space. Okay, simple. Same as in case of electric field. In case of electric field it was epsilon by epsilon naught. Same as your electric field, we are using the same symbols, similar meaning. Okay, mu R equals to 1 plus chi is a dimensionless quantity called relative magnetic permeability. Very important, relative magnetic permeability of the substance. It is along the dielectric constant. Sorry, it is analog to of the dielectric constant. I said this is same as dielectric constant, right? It is analog to the dielectric constant in electrostatics, right? The magnetic permeability of the substance is mu and it has same dimension as units of mu. Okay, mu naught. So mu and mu naught are cousin brothers. So for example, when there was vacuum, there was no medium or there was air, we use mu naught. Okay, but if there is no air, when we are using some other material, that material is no longer having the same permeability as air, so that will have a different permeability. That permeability is mu. Okay, now let's look into, now here it is normal mu. Okay, mu equals to mu naught mu R, obviously, right? So mu equals to mu naught mu R equals to we know that mu R is 1 plus chi, right? So let us use this formula. Now we can write this as the three quantities chi, mu R and mu are interrelated. Obviously you can see that mu equals to, what is the formula then? Mu equals to mu naught 1 plus chi, right? So now chi also, this is equals to mu naught mu R. You might think which one is independent, which one is dependent. So now you should remember that only one of them is independent. Okay, not everything is independent, only one of them is independent. That means one will be given to you. You can calculate other two variables because mu naught is a constant, right? Mu naught is a constant. Mu naught is 4 pi times 10 to the power of minus 7. So if suppose mu is given to you, you can simply calculate chi by dividing that mu with mu naught. Similarly, if mu r is given to you, you can calculate chi and mu as well. Okay, so all the other quantities can be calculated if one of the quantity is given. Okay, given one, okay, the other two may easily be determined, right? So as I said, if one is given, you can calculate the other, right? Now let us look into a simple problem. Okay, it is not an MCQ problem, it is a step-by-step solution. So let's look. A solenoid has a core of material with relative permeability 400. Okay, but this is a very important concept, so that's why I am solving it this question. Maybe in your KCET exam or maybe in your board exam, the similar problem may come, okay, with the multiple choices, so you should be ready. Okay, the windings of the solenoid are insulated from the core and carry a current of 2 ampere. Okay, so relative permeability is given. Okay, mu r is given. Mu r is 400. Okay, and the current is given 2 amperes, right? Carry a current of 2 amperes. If the number of turns is 1000 per meter, so number density is given, small n itself is given. Okay, 1000 per meter. Calculate H, M, B and the magnetizing current M. So this is very important for KCET, this part, magnetizing current. Okay, they might ask this question. This is from your NCERT book, so they might ask this question, but if you ignore this question, you will not be able to answer. So first of all, what is magnetic field? We know that magnetic field in free space, when there is nothing, magnetic field was given by mu naught Ni, right, for a solenoid. For a solenoid, magnetic field was given by mu naught Ni. So here B equals to, instead of mu naught, we have to use mu Ni, right? And H is given by B by mu. You should remember this. H is given by B by mu. So we can write H is basically Ni. Now let's put the value of N. N is 1000, right? And I is given 2 amperes. So H is 2000. Unit is ampere per meter or ampere meter inverse. Okay, so ampere meter to the power minus 1, whatever you like. Okay, ampere per meter, I say ampere per meter, but when I write ampere meter to the power minus 1. Okay, this is the modern way of writing the units. Okay, this is part A. Now let's calculate M. Okay, M is given by mu r minus 1 times H, right? So we have already learned this. Mu r is given by 400 minus 1. H we have calculated 2000, right? Now if you see, it will be 399 times 2000. Okay, now if you keep that number as 400 only, okay, you can get an approximated value. Approximated value will be 400 times, so approximately you can write this as 400, as it will not change the result by much. Okay, so it will be 8 times 10 to the power of 5. 1, 2, 3, 4, 5. Okay, 8 into 10 to the power of 5 ampere per meter. Okay, because 400 mu r minus 1 is an unitless quantity. Now what else was asked? So what else was asked? They have asked you B also. Okay, B formula, we have already know B formula. So let's use that formula and calculate B. Okay, so B is mu Ni, right? Or mu is what? Mu is mu naught, mu r, Ni, right? Now mu naught is 4 pi times 10 to the power of minus 7. Okay, also mu r is 400 and Ni we have already calculated. If you see Ni we have already calculated, that is coming out to be 2000. So you can directly use that, or you can use the individual values whatever it is. I am simply writing 2000 because I know Ni is equal to 2000. Now let us calculate the values. Okay, 4 4s are 16, 16 2s are 32. So 32 pi, okay, 10 to the power of minus 7, 1 2 3 4 5. So minus 7 plus 5 minus 2. Okay, now 32 pi means 3.14, okay, times 10 to the power of minus 2. Now what is 32 times 3? 32 times 3 is 96, okay, but if you know that there is a 0.14 also, so we can approximately take this value as 100. Okay, you can calculate this value. There is one way to calculate this, that 33.33 times 3 is 100, right? Similarly, it is not 33.33 but 32 is here and 0.14 extra in the multiplication. So approximately you can take this value to be round figure to be 100 and minus 2. So minus 2 is basically divided by 100, right? So 100 divided by 100 is basically 1 and unit is Tesla. Okay, so you need to remember that. So magnetic field comes out to be 1 Tesla. What else they have asked you? They have asked you to find the magnetization current. This is part B, this is part C. Part D is magnetization current. Magnetization current means if there was no such material present inside the core, okay, no such material is present, only air is present, then how much current it would have required to get the same amount of magnetic field. You need to remember this concept. Magnetization current means if there was no magnetic material present inside the conductor, inside that solenoid, then how much magnetic current would have required to get the same magnetic field. So we know the formula, B equals to mu naught Ni, okay, and I am saying this is the magnetization current. Okay, now what is B? B is 1 Tesla, we have already calculated, so we will put that value 1 Tesla. Mu naught is 4 pi times, or what else you can do, instead of using this, you can, instead of writing that, let me use one more shortcut trick. Okay, so the formula that we received, B was 32 pi 10 to the power of minus 2. So I will use that value, so that pi etc cancels. We do not need to go down to that calculation level. So this is magnetic field, right? 32 pi. Okay, now mu naught is 4 pi times 10 to the power of minus 7. N is 1000 and we are trying to find this magnetization current. Okay, now I will use this part of the board. So pi cancels, 4 is the 32, so 8, this is part D, right? 8 times 10 to the power of minus 2 equals to 1000 times 10 to the power of minus 7. So 1000 times 10 to the power minus 7 is 1000 times 10 to the power minus 7 is equals to 10 to the power of minus 4 times Im. Okay, so Im is basically 8 times 10 to the power of minus 2 divided by 10 to the power of minus 4, that is 8 times 10 to the power of 2, that is 800. So you imagine that the magnetic field that we achieved using only 2 ampere current with certain material, okay, now we need 800 ampere current to achieve the same magnetic field, which is absurd. That's why whenever we are using solenoid, we don't use if you don't use any material at the core, then our entire effort is getting wasted. So the same magnetic field to achieve you need 800 amperes when you are using air, and you need 2 ampere currents when you are using some material having a relative permeability of 400. So you can imagine, and this current is absurd. It is not possible to get 800 ampere current. That will be like a huge current, and if you pass this current, the circuit will blow up. Okay, so that is a huge current. 2 ampere current itself is little higher, but still it is manageable, but 800 amperes is absurd. Okay, so that is why this this concept is very important. Now we are moving into magnetic properties of materials. Based on the properties of material, we classify magnetic materials into 3 parts. First is diamagnetic. Okay, what is diamagnetic material? Diamagnetic substances are those which have tendency to move from stronger to the weaker part of the external magnetic. Very important. Generally what we see if we apply a magnetic field, objects generally tend to move from weaker part to stronger part, right? That is getting attracted towards it. But these materials, okay, they tend to move from stronger to the weaker part of the external magnetic field. Okay, in other words, unlike the way a magnet attracts metals like iron, it would have repelled the diamagnetic substance. Though the repulsion is very weak, you will hardly notice it, but if you apply a magnetic field, then that magnetic field, instead of getting into the material, it will slightly getting repelled. Okay, small amount of repulsion will happen. Okay, very salpa amount of repulsion will happen. You will not be very easily detectable, but instead of getting attracted, it will be actually repelled by the magnet. So it is a anti-magnet, you can say. Okay, now the simplest explanation for diamagnetism is as follows. Electrons in an atom orbiting around nucleus possesses orbital angular momentum. So when we see an atom, an electron rotating around an atom, suppose there is a nucleus, it possesses orbital angular momentum, right? It's rotating, so this will have some spin. You have learned in chemistry, up spin, down spin. So what is the meaning of the spin? So it is spinning around its axis, so it has a angular momentum, right? So angular momentum is there. Okay, we know that angular momentum is r cross mb, right? So they have mass, they have velocity, and they are rotating in a circular path, or whatever orbit it is, elliptical orbit, circular orbit. Okay, they have an angular momentum. Now these orbiting electrons are equivalent to current carrying loop. I already told you while I gave the explanation for the first part. Okay, current carrying loop, and thus possesses an orbital magnetic moment. Okay, there is a magnetic moment associated with this motion. Okay, I already told you that. Now diamagnetic substances are those ones which resultant magnetic moment in an atom is 0. So normally the magnetic moment in this atom is 0. So if there is a 1 upspin, there should be someone who is cancelling it in downstream. Okay, downspin. So total net magnetic moment will be 0. Net magnetic moment in that atom will be 0. Okay, so if there is an up spin, there will be a down spin. So if there is an up spin, there will be equal and opposite down spin. They are cancelling each other. Okay, let me know, don't confuse it. Let me clearly draw this so that you don't get confused while seeing the note. So suppose this is an atom. Okay, this is nucleus, positively charged nucleus. One electron is rotating up spin, one electron is rotating down spin. Okay, now because of one of them is there is a upward magnetic moment, and for another there is a downward magnetic moment, and the resultant is 0. Resultant magnetic moment is 0. Okay, now when the magnetic field is applied, now if you apply some magnetic field, okay, suppose you have applied some external magnetic field B, okay, then these electrons having orbital magnetic moment in the same direction. So in this case, this and this have same direction, right? They will slow down. Okay, very important, they will slow down. In the same direction, slow down, and those are in the opposite direction, speed up. Okay, so whoever is in the same direction, they will slow down, basically reducing the try to reduce the external magnetic field. Similarly, whoever is opposing that, they will increase. Okay, they will have some freedom. Whoever is supporting that, they will slow down. Okay, whoever is opposing them, they will get stronger, and thus it will reduce the overall effect of the external magnetic field. Okay. Now next is paramagnetic substance. Paramagnetic substances are those which get weakly magnetized, very weakly magnetized when placed in an external magnetic field. So they are getting attracted by the magnetic field, but very weakly. Okay, they have a tendency to move from a region of weak magnetic field to strong magnetic field. As I said, they get weakly attracted to the magnet. Now if you draw the magnetic field lines, okay, you will see they are slightly, magnetic fields are going in by a small amount. Okay, magnetic fields are going in a small amount. Okay, now what else? Last but not the least is ferromagnetic. Now one important example of paramagnetic substance is oxygen molecule. Oxygen molecule is a paramagnetic substance. There is an explanation for that, but I am not going to discuss that. The discussion may happen in your chemistry, but not in physics class. Okay. Now ferromagnetic substances are those, this is the most important concept, okay, are those which get strongly magnetized when placed in an external magnetic field. Okay, they have strong tendency to move from a region of weak magnetic field to strong magnetic field. That is, they get strongly attracted by a magnet. So suppose we have kept one ferromagnetic substance in a magnetic field, and we apply a magnetic field. Okay, when we apply a magnetic field, it will get strongly attracted. It will get strongly attracted towards the magnetic material, ferromagnetic material. Okay, let me use a different color. So what will happen? They will strongly attract. Everything will be, even far magnetic field lines will be getting attracted. Okay, everyone will concentrate here with a high density. Okay, the density of the lines will be very high here. Everyone will try to go inside this material. Okay, so they will try to get inside the material. Okay, even they are not coming in, they will try to come towards this. Okay, so if every magnetic field lines will try to move inside this material. Now if the magnetic material is depending upon different types of ferromagnetic material, how much they can accommodate, that is also there. We will see that as well. Now individual atoms or ions or molecules in a ferromagnetic material possesses a dipole moment as in a paramagnetic material. We have seen that in paramagnetic material they also have a dipole moment, but they have a net dipole moment, right? Now however, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called domain. So let us understand what is the meaning of that. So each atom has the dipole moment. Now all the atoms in this zone, they all made a party. Okay, we are a party. I have formed a party and we have one direction only. But the next neighboring state, okay, they said, okay, I don't care about your party, I have my own party. Right. Similarly, all the regions, instead of having only atomic level, so atomic level is one. Okay, atomic level is one, only you are considering one atom. Okay, it is very difficult to consider all the atoms, but sometimes some atoms they combine together and they form a single directional area. They are called domains. Okay, this is a domain. Domain can vary from size and shape, does not have any fixed size and shape, but this is when no external field is applied. In this case, B applied is 0. B is 0. Now in that case, they are randomly oriented. Even though they have individual magnetic moments, the net magnetic moment of all these domains are 0. When you add them, all of them up, you will generally get 0 magnetic moment. Now when you apply some magnetic moment, external magnetic field, they all align quickly. You remember something what I have shown you some similar things in another chapter. Yes, capacitance chapter, dielectrics, they are also like this. They have some of them already have an electric moment, dipole moment, some of them don't have, but when the external field is applied, they all align. In this case, only ferromagnetic material, they align when external magnetic field is applied. They align in the direction of external magnetic field. All the domains are now lined up, ready for prayer. Okay, so this is the chaotic scene inside the class when some students are grouped together. They are saying, okay, this is my friend, he is my friend. Okay, I will not listen to whatever others are saying. We will sit behind the bench, or we will sit on the right side of the bench. We will sit under the fan, right? And as soon as the teacher comes, everyone is aligned, everyone is sitting together quietly listening to the class. Same thing is happening for ferromagnetic material as well. Okay, be ferromagnetic, don't be diamagnetic. What happens when external field is removed? Now what will happen? You have applied external field, they are all aligned. Now what will happen? If you are a ferromagnetic material, some ferromagnetic material, the magnetism persists. Okay, even after teachers left, the students are still sitting in their benches. They are still waiting for next lecturer to come, and they are patiently waiting. Okay, so they are good students, the best class in the college. Such materials are called hard magnetic materials. Okay, the best students. So hard magnetic materials, okay, they do not change their orientation even after you remove the magnetic field. Okay, or called hard ferromagnets. Okay, there are few examples. Alnico, aluminium and cobalt, alloy of aluminium, nickel and cobalt. Okay, Al aluminium, Ni nickel, Co cobalt. Okay, an alloy of iron, aluminium and nickel. Iron is also there, even though it is not directly mentioned in this name. Okay, aluminium, nickel and cobalt, and copper is also there, is one of the such material. So Alnico is one of the material which actually is a very good hard magnet. If you convert it into a magnet, it will stay magnet. Another one is neodymium. Okay, you have heard, I asked you a question in our previous class that name one material which is a very strong magnet. Yes, neodymium is one substance which is a strong magnet. Okay, and once magnetized, it remains as a magnet for a long time. Okay, the naturally occurring lodestone. Okay, lodestone is one of the very crude magnet. Okay, it is used for a very long time in history. Such materials form permanent magnets to be used among other things as a compass needle. Okay, they are used as permanent magnets. So if you are doing any experiment in your physics lab using a permanent magnet, they are possibly one of these materials. Okay, they are basically one of the strongest magnet, and also they are used as compass needle. Okay, so nowadays you may have seen compass inside your mobile phone. Okay, but in the past there was compass which was actually physical compass which you can hold. It is still available. You can ask your teacher in physics lab, sir, show me a compass. They have compass. They will show you a compass. In some museums or some homes also, people use it as a decorative item, a compass as a decorative item. Okay, but it is also possible using one of this material. What happens when the external field is removed for some materials? Okay, in which magnetism disappears on removal of the external field. So as soon as teacher leaves the class, the student starts shouting. Okay, they are whole chaotic again. Okay, but this is also true for some materials. Okay, the soft iron is one such material. They also have some uses. Okay, instead of permanent magnets, soft magnetic materials are also have some use. Appropriately enough, such materials are called soft ferromagnetic materials. Okay, now any electromagnet, when you are constructing an electromagnet, basically you prefer a soft magnetic material. Also inside a transformer, we will see later on when we will study transformer in our next chapters. There we will see transformer also have a soft iron core. That is because it's a soft magnetic material. When you switch off the magnetic field or you reverse the magnetic field, okay, they are very swift, they are very nimble, they can change their orientation quickly. So that is why they are called soft magnetic material. Okay, there are a number of elements which are ferromagnetic. Okay, iron, cobalt, nickel, gadolinium, they are all ferromagnetic in a normal room temperature. Now out of that, gadolinium is a very interesting material. Okay, we have done some experiments when I was doing my masters in physics. Gadolinium was a ferromagnetic material, and its Curie temperature is unfortunately deleted from your syllabus. Okay, Curie temperature was within the room temperature. So it shifts from paramagnetic to ferromagnetic around 21 or 20 degrees Celsius. So we were doing this experiment during a hot summer, so we have to use ice to cool down the temperature of the sample, and then we can check how it is getting changed from a paramagnetic to ferromagnetic. So the very interesting substance. Okay, it's QD temperature. Generally all other QD temperature is very high. Okay, iron, cobalt, nickel, they are some of them are in thousands of degrees. Okay, some of them are 100 of degrees, 200, 300 degrees. But gadolinium is one substance which has around 21 degrees Celsius as their QD temperature. So it shifts from paramagnet to ferromagnet at room temperature. So you can observe it. Okay, in cold, suppose you are visiting a cold country, there you might find a gadolinium which is a magnetic material. But if you visit another country, you take that magnet, buy that magnet and visit a warmer country like India, there you will find gadolinium is, that magnet is no longer working, because it is now above QD temperature, it lost its magnetic property. So that is very interesting story. Now let's move on. The relative magnetic permeability of ferromagnet is greater than 1000. Okay, so we will see in a table of comparison what is the meaning of all these things. Now let's look into this question. In a permanent magnet at room temperature, domains are partially aligned, domains are all perfectly aligned, magnetic moment each of the molecule is 0, the individual molecules have non-zero magnetic moment which are all perfectly aligned. Now you should remember that a domain cannot, all the domains cannot perfectly align even if this is the very strongest magnet, because all the molecules, all the atoms are constantly vibrating at temperature. Only they can be aligned at absolute zero temperature, very close to absolute zero temperature. They are called super magnets, okay, superconductors. So at room temperature it is not possible. At room temperature, that means around say 25 degrees Celsius or 30 degrees Celsius, all the atoms, all the molecules are still vibrating. So domains are partially aligned. Domains cannot be all fully aligned. So domains can only be partially aligned. So correct option is option A, domains are partially aligned. Okay, now diamagnetic, paramagnetic and ferromagnetic substance. So in case of diamagnetic substance, chi is basically magnetic susceptibility is greater than -1, but it is less than 0. So it is negative, in the range of negative, but it is not too much negative, it is only slightly negative. Now for paramagnetic substance, it is positive, and it is not too much positive, it's slightly positive. Okay, here epsilon is a small positive number. Okay, it's a small positive number. It varies from material to material, so you cannot give it a particular fixed value. Also it depends on temperature. For ferromagnetic material, susceptibility is very high. Okay, similarly the relative permeability for diamagnetic material is between 0 and 1. Okay, for paramagnetic it is between 1 to 1 plus this small value, and ferromagnetic it is very greater than 1. Okay, and for diamagnetic its permeability, actual permeability is less than permeability of free space. Okay, if you see in electrostatics, all the other material has permittivity greater than that of the free space. But in case of magnetism, you find some materials which has a negative permeability. Okay, you can say this is a negative value, that is less than that of the free space permeability. Okay, that is not possible in electrostatics, one important point. Okay, in paramagnetic substance, mu is greater than mu naught. Obviously mu is not slightly greater than, but in case of ferromagnetic it is very greater than mu naught. I think I have solved this question. Now let us look into the time period and of an oscillating magnet. Okay, time period of oscillating magnet. When you take one magnetic needle, okay, and you apply some external magnetic field, then it starts oscillating. If you rotate it, it starts oscillating, and the expression for time period is given by 2 pi I square root of I by mb. Here I is moment of inertia, m is magnetic moment, b is external magnetic field. Now remember, this formula was a part of the previous syllabus where Earth's magnetic field was involved, and here we used to write BH because we are only oscillating it in under the Earth's magnetic field. Now even though the Earth's magnetic field is deleted, and this formula still can come as a application of oscillation. Okay, this formula still can come as an application of oscillation, and because this formula is still valid even if there is no Earth's magnetic field, even if there is only an external magnetic field is there, external magnetic field is still in our syllabus. So let's look into one question that came in a previous year. There is no if there is no torsion in the suspension thread, then the time period of a magnet executing SHM is, obviously you have seen, it is 2 pi I by mb. So correct answer is 2 pi I by mb. Now this is the homework question for today. You can take the screenshot or you can pause the video, solve the question, mention the answer in the comment below. Okay, I'll move forward to the next question. This is the second homework question. You can again pause the video, take a screenshot, whatever you like, answer it, mention the answer in the comment below. And there is a dedicated playlist available where you can get all the lectures that we are doing in this channel in this subject, physics subject. For physics subject there is a particular playlist available. You can go and check at your own pace at any time if you want. Also the lectures note will be available in the description below. So each lecture you can download from previous videos. All the lecture notes are available in the videos. You can go watch the video, click on the downloading link, and you can get the notes for that lecture video. Okay, and also join our WhatsApp channel for all the latest news, latest updates that is happening on our channel. And if you think we are making any changes to your life, you can subscribe to our channel and like this video. Thank you.